Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutiwa Sos, Ugobela Maths. And without any further ado, let's look at these questions that we have here. Okay, so we have question 9. It says the diagram represents a simple generator. The coil is rotated in an anti-clockwise direction. Then 9.1 says, does the diagram represent an AC or a DC generator? Suggest the reason for the answer. Right. Okay, so let's look at this. We know that an AC would have slip rings, commutators, and a DC would have split ring. Looking at this, we can see these are what? These are slip ring commutators. So that means 9.1, we are supposed to say this is an AC generator. Right. And the reason for that, AC generator, this has what? It has slip rings. It has slip rings, right? Then 9.2 says, state the energy conversion that takes place in this generator. This is a generator, so we know a generator would have to take a mechanical energy to electrical energy. Right, so you get the mark for that. Then that's it. Then 9.3, they say for the parts labeled A and B in the diagram, write down their name. So what is the name of these parts here? So as we can see, these are what? These are the carbon brushes. So these are brushes or carbon brushes. So carbon brushes. And then what is their function? So the carbon brushes ensures conductivity between the slip rings, ensures conductivity between the slip rings and the external circuit. Right. So this is a very simple topic, guys. You just have to collect marks like that. Then 9.4, they say, the part XY of the coil is about to move upwards. As soon as it moves upwards, will the induced current flow from X to Y or from Y to X? Now note that this is a generator, right? They say the part XY is about to move upward. So this means that this is going in a what? This is going in an anti-clockwise direction, right? So if it's going in an anti-clockwise direction, we know with the generator, if the coil is rotating anti-clockwise, then it also means that the current would have to flow in an anti-clockwise direction, right? So that means this is the current that will be flowing in an anti-clockwise direction. So that means it will be moving in which direction? Will the induced current flow from X to Y or Y to X? We are supposed to say X to Y, following that anti-clockwise direction. So note that with the generator, so this is very important to note, with the generator, if it's flowing, if the coil is anti-clockwise, then even the current will be anti-clockwise. Right. And then again, if the coil is rotating clockwise, then that means also the current will be flowing clockwise. Right. So that's what you need to note. But then with the motor, that thing is opposite. If the coil is moving anti-clockwise, then the current is clockwise. And if the coil is clockwise, then the current is anti-clockwise. But that is with the motor. So you will see as we continue with these questions here. Now, 9.5 says the peak voltage supplied by this generator is 120 volts, right? So that's the peak voltage. Is in the position that the coil is shown. So this is the what? The vertical position. The vertical position. In the position in which this is shown, will the output voltage be 0 volt, 85 volts, or 120 volts? Now you need to understand in the vertical position, that's where we have the minimum voltage, right? So that's where we actually have a voltage of 0 volt. So the minimum is just 0 volt, right? So in the vertical position, that's where we have the minimum voltage of 0 volt. Then in the horizontal position, that's where we say the coil will produce the maximum current. So the maximum current and maximum voltage. So this is where we would have the maximum voltage. In this case, it would be the 120 volts, right? So looking at that, we can see that it is in the vertical position as shown on the diagram. So that means the correct answer here would have to be what? For 9.5.1, we would have to say 0 volts because it is in the vertical position. And at the vertical position, the voltage is 0 volts. Okay, nice. Then that's it for that one. So we've been collecting marks like that. And then, okay, now we have the RMS value of the current supplied to the external circuit is 1.2 amperes. Define the term RMS for an alternating current. So this is how we define it. Very simple. You say this is the RMS. So RMS for alternating current. RMS for alternating current is the AC current that dissipates the same amount of energy as an equivalent DC current or direct current. Okay, so that's how you actually write it. So RMS for an alternating current is the AC current that dissipates the same amount of energy as an equivalent DC current, right? So that's how you are supposed to define that. Then 9.5.3 says calculate the average power output of the generator. So we are given the current here, and then let's see, they say this is the RMS value. So you need to always be careful in terms of checking whether the current that is given is a maximum or RMS. If it is a maximum, then we know that we need to first convert it using this formula. IRMS is equals to Imax over root 2, right? So always be careful of that. So, okay, in this case here, we can see that we are just given the RMS here. So this is the IRMS. So no problem with that. And then they say calculate the average power output of the generator. But then remember that from the statement here, remember, these are all sub-questions for 9.5, right? So they say the peak voltage. What does the word peak mean? Peak means maximum. Maximum, right? So the maximum voltage supplied by this generator is what? 120 volts. So that means we can't use this maximum voltage. We would first need to convert it to VRMS. So that means here we need to say VRMS is equals to Vmax over root 2. Now our Vmax is 120 divided by root 2. So you will just quickly punch it into your calculator there. And then that will give us a value of VRMS of 84.85 watts, rounded off to 2 decimal places. Then we have our P average is going to be, so from the formulas that we have for power, we can say that if we are given IRMS and also VRMS, then the formula that we'd have to go with is VRMS multiplied by IRMS for the average power. Then this is 84.85. Multiply that by the 1.2, right? And then if you multiply that, so let's multiply, this is going to give us 101.82 watts, right? So do not forget the SI unit for power. And just like that, you would have scored yourself 4 marks. So not a very difficult question. That's what you needed to do there, right? So, okay, let's look at the following question. All right, so we have another question 9 here. It says a simplified diagram of an electric machine is shown below. And then as we can see, that's it right there. 9.1 saying, is this electric machine a generator or an electric motor, right? So let's look at this. We know that with a motor, we are expecting to have a power source, right? Some form of a cell or a battery there. So looking at this diagram, we can see that there is no power source whatsoever. So we have to just assume that it is a generator, right? Because remember, a generator is the one that will produce the electrical energy, right? So, okay, then we are going to say 9.1, this is a generator. And then our reason for that, it has no power source. It has no power source, right? Then 9.2, they say write down the names of the components labeled A, B, C, and D. Now we can see that this is just one mark. So it's not like A, B, C, and D have individual names, right? So this is just one name. So all this, the A, B, C, D represents one component, right? And what is this component known as? It is known as the coil, right? So they tried to confuse you there by saying names, but then it is just a name. That's just one component. 9.3 says, give a reason why carbon is preferred over iron for the brushes in electric machines. It's because carbon is a good conductor of electricity. Carbon is a good conductor of electricity. So that's why it is preferred, right? Remember the carbon brushes, the function of the carbon brushes is to ensure what? Conductivity between the slip rings that we are seeing here and the external circuit. So we need something that is a good conductor of electricity. So 9.4, in which direction is the current flowing? Again, we said this is a generator. And then we know with a generator, if this is rotating in a clockwise direction, that means current must also flow in a clockwise direction, right? So we have stated that in the previous question. So that means here is the current flowing from A to B or B to A. The clockwise direction would have to be from A to B. There we go, 2 marks. Then 9.5 says the graph below of a voltage versus time was obtained from an alternating current generator. They say 9.5.1, calculate the frequency of this voltage, right? So taking us back to that formula. So to calculate the frequency, we know that frequency is 1 over the period, right? So remember, we are working with a graph here. So that means we have to consider the period is the time taken to form a complete cycle, right? To complete one full cycle. So if half a cycle is completed in 0.01 seconds, that means to complete a full cycle will be 0.02 seconds. So this value that we are seeing here is what is known as the what? The period. And the period is represented by the symbol T, right? So that means to calculate our frequency, we just simply need to say 1 over 0.02. And then you simply punch all of that in your calculator. So that's 1 divided by 0.02. And then we get what? 50. But then what is the SI unit for frequency? Hertz, Hz. Right. So just like that, we have our 2 marks right there. Okay, then we have 9.5.2. It says calculate the average power generated if the generator produces a maximum current of 2 amperes. Okay, so let's have a look at that one. 5 marks. So this is a very serious question. So, okay, now let's check first. We are given a value here of 250 volts, which we already know if we are given a graph, the value over here represents the what? The peak voltage, right? Remember, peak means what? Maximum. So that represents the maximum voltage, right? So we are also given the maximum current as well. So in order to calculate the average power, we do know that the formula for average power goes as this. So power average is equals to VRMS and then multiplied by IRMS. Looking at this formula, we can see that we do not need to use the maximum current and also, the maximum voltage and also the maximum current. We do not need to use those. So first thing that we have to do is convert those two values into RMS, right? So first we can start with the maximum voltage converted to VRMS. So by using this formula, so we're going to have 250 over root 2. Then in your calculator, Just go 250 divided by root 2, right? So this is going to give us 176.78 and then volts, right? Then IRMS is equals to what? Imax over root 2. So this is going to be 2 over root 2. And then when we punch that into our calculator, 2 divided by root 2 is going to give us 1.41 amperes. Then to calculate the average power, it's simply a matter of writing that formula and substituting into that formula now that you have both the VRMS and the IRMS. So let's see now. So that's 176.78 multiplied by 1.41. And then this is going to give us what? 176.78 multiplied by 1.41. So this gives us an average power of 249 point, round off to 2 decimal places, 26, right? Watts. So let's not forget the SI unit. So just like that, you would have earned yourself 5 marks. So always make sure that you check whether you are given the maximum current or you are given the maximum voltage. And if you are given those, always remember to convert to the RMS values, right? So that's how you are supposed to tackle this question, all for a total of 13 marks. Okay, so let's move on to the next question, right? So this is basically how you practice, guys. Make sure that you do as many questions as possible so that you get to understand the trend of the questions. And the more questions you do, the better it is to answer those exam questions. And then the less anxious you are when it comes to answering your exams or writing your exams, right? Okay, so we have another question 9 here. The third question 9, it says the diagram below shows the voltage output of a generator. And then as we can see here, we have our graph like that. So this is representing 1 full cycle and a half, right? So this is 1 full cycle. This would be the period over here, the time taken to complete 1 full cycle, and this would be half a cycle, right? Now 9.1 says, does this generator have split rings or slip rings? Now looking at this, we can see that this shape here is normally the one that we get for AC, and then this is the shape that we normally have for a DC. Right, so by just looking at the graph, we can tell that this has to be an AC. And then what do we know about AC? We know that AC has what? Slip rings, right? So that means our answer for 9.1 has to be slip rings because this is AC. Okay, then 9.2 says, which one of the diagrams below, A or B, shows the position of the generator's coil at time A is equals to 0.10 seconds, right? Now, we have already spoken about that to say that if we ever produce 0 volts, right? If ever the current or the voltage that is being dissipated there is 0 volt, then we know that our coil is in the vertical position. So in the vertical position, that's normally where we have the minimum voltage, right, of 0 volts. And then at the horizontal position, that's where we have the maximum voltage. And then in this case, our maximum voltage is 312 volts. Now, do not be confused to say that the negative 312 volts is the minimum. This is not the minimum. This is still the maximum voltage. It is just the maximum voltage in the opposite direction. Because remember, the coil is doing a 360 rotation there. So that means at some point it will be rotating in the opposite direction. Hence, we have this negative 312. But then that is still the what? The maximum voltage. Okay, so we are then going to say that where we have this at 0.10 seconds, 0 volts, it has to be diagram B because that's where it is in the vertical position, right? So that's where it will produce 0 volt of voltage. Then 9.3 says, calculate the root mean square So root mean square is RMS shortened. So we want the RMS voltage for this generator. So we are just going to say VRMS is equals to what? Vmax over root 2. So what is our maximum? Our maximum, we can see it right there, the peak voltage. So this is 312 over root 2. So in your calculator, you just quickly punch that. So you go, this is 312 divided by root 2. And then this is going to give you what? 220.62 volts, right? Then 9.4 says, so 9.4.1. So we are told the statement, a device with a resistance of 40 ohm is connected to this generator. Calculate the average power delivered by the generator to the device, right? So since we are given resistance here, and then we have also calculated the VRMS, that means the formula that we'd have to use here is the one that goes P average is equals to V squared RMS over R. So whereby we'll now put the VRMS as 220.62 and then square it. And then down here, we put our resistance of 40, right? So let's see. We have the 220.62 squared and then divided by 40. This is going to give us 1,216.83 watts, right? So there we go. That's our average power. Then to calculate the maximum current right now, this is what we are supposed to do. So we already have the power average, meaning we can use one of these formulas. Power average is VRMS multiplied by IRMS, or we can use P average is equals to I squared IRMS over multiplied by R, right? So either one that you prefer. So let me just go with this one because we hardly use it. So P average is equals to I squared IRMS multiplied by R. Now we have calculated the average power, 1,216.83 from the previous question. And then we have our I squared IRMS. Then what is the resistance? Still use the 40. Then we're going to divide by 40 both sides like that. So this is going to be I squared IRMS. And then in order to get rid of this square, 1,216.83 divided by 40, let's just square both of them. So I'm avoiding to just have rounded off values before the final answer. So I'm just going to punch all of that same time. So this is going to give us an IRMS of 5.515500 in a whole lot of decimals. So I'm not going to round off as yet. Then I want the maximum current. So the maximum current will be IRMS is equals to Imax over root 2. Then this is going to be the 5.555500, whole lot of decimals, Imax. So you're just going to keep it into your calculator and then you just go answer multiplied by root 2. So you save the answer in your calculator and just go multiply by root 2. So this is now going to give us what? 7.8. Exactly 7.8 amperes. Right. So there we go now. Okay, so here we have another one, question 9, the fourth question. So it says the simplified diagram below represents a generator rotated in the direction shown on the diagram. 9.1.1 says state the energy conversion that takes place in this generator. This is a generator, so we already know the energy conversion is what? Mechanical energy to electrical energy. Mechanical to electrical energy. Then 9.1.2, they say the generator is rotated clockwise as indicated in the diagram. What is the direction of the current in the section PQ of the device? Write down only P to Q or Q to P. So this is rotated clockwise, and since it is a generator, we know that the current should also as well flow clockwise. right? So if it flows clockwise in this section, it's going to be P2Q, right? So that's how you answer those questions. Then 9.2 says, the diagram below shows a simplified version for part of a household wiring circuit. The voltage supply in a certain house is 230 volts. A light bulb having a resistance of 12 ohms. So let's highlight there. The voltage supply in a certain house is 230 volts. A light bulb having a resistance of 12 ohm and a kettle having a resistance of 24 ohm are used at a certain time as shown in the diagram below. Now understand that the voltage supply in our household is always the RMS. So voltage is being supplied in RMS, current is being supplied in RMS. So what you are given there is not the maximum, it is the VRMS. Hence in 9.2.1, we can see that asking us to calculate the peak voltage. So had they given you the peak voltage, they would just say write down, right? But then from here, we can see that they want us to calculate that maximum voltage, which simply tells us that the voltage that we are given here is not the maximum. It is the VRMS. So 9.2.1, again, use the same formula. It's a 3-mark question. Formula, substitution, correct answer with the correct SI unit. So Vmax over root 2. So we put our 230 here is equals to Vmax over root 2. Then we simply just have to cross multiply here. So umshini weibalo, your calculator. So 230 multiplied by root 2. This is going to give us Vmax is equal to 325.27 volts, rounded off to 2 decimal places. Right, so 3 marks like that. Then 9.2.2 says, for 5 marks, calculate the average power dissipated if the 2 light bulbs and kettle are used at the same time. Right, the 2 light bulbs and kettle are used at the same time. Okay, so in this case, we're going to assume that they put another light bulb here of the same resistance in parallel. So this will still be 12 ohm. So note that they said 2 light bulbs and a kettle. So this is our kettle having a resistance of 24 ohms, and this our 2 light bulbs. Right. In this case, that means the first thing that we'd have to do is calculate the effective resistance of this parallel resistors, right? So this is 1 over Rp, 1 over R1 plus 1 over R2 plus 1 over R3, right? So we are going to have 1 over 24 plus 1 over 12 plus 1 over 12. Now we know that in order to calculate Rp, we would have to take all of this, add them together, and then inverse them to the exponent of -1. So in your calculator, umshini weibalo, remember that's how we calculate the effective resistance of a resistors connected in parallel. So this is a concept from electric circuits. So 1 over 24 plus 1 over 12 plus 1 over 12, and then all inside the bracket to the exponent of -1. So our resistance of parallel will be 4.8 ohms, right? So now, after getting this 4.8 ohms, we need to still calculate the what? The average power now. So note that we are given the VRMS as 230 there. So that means the formula that we can now apply to calculate the average power, simply saying V squared IRMS over R, right? So this is power average is equals to 230 square divided by what? A resistance of 4.8. Then let's calculate the average power dissipated. So this is going to be 230 square divided by what? 4.8. So we have 11,020.83 watts. So that's how it goes. Nice one. So again, 11 marks in the bag, and then that's how you were supposed to tackle this question right here. So let's proceed to another question. All right, we have another question 9, a fifth question. Then a simplified diagram of an electric generator shown below. When the coil is rotated with a constant speed, an EMF is induced in the coil. Then 9.1.1 says, is this an AC generator or a DC generator? Right. Now, looking at the commutator that we have here, we can see this is a what? A split ring commutator. So that means this is what? This is DC. So this is a DC generator. Because of what? The split ring commutator. Then 9.1.2 says, briefly explain how EMF is generated in the coil, right? How is EMF generated in the coil? So, okay, so this is, we know that a generator works with the principle of electromagnetic induction, right? So that means we just have to explain this based on the electromagnetic induction. So we're simply just going to explain this by saying EMF is induced as a result of the change in the magnetic flux linkage with the coil. So you will still remember this from this formula that we used to do in grade 11, which was like this. So EMF is induced as a result of the change in the magnetic flux linkage with the coil, right? So we know that the change in magnetic flux linkage is directly proportional to the EMF induced. So we just simply say, because briefly for 2 marks, we can just put it like that. EMF is induced as a result of the change in the magnetic flux linkage with the coil, right? Okay, so for the sketch, you just go like this. Draw a sketch graph of the output voltage versus time for this generator. Show one complete cycle. You just go like, this is it. So remember we said this is DC. So DC must go like this. And then there we go. That's a complete cycle. Then it's just a matter of labeling your axis. So here you will have your time in seconds. And then right here, this will be the potential difference of voltage. So let's write potential difference. They said output voltage versus. So let's just say output voltage here. And then given in volts. So that's your 0 right there. Okay, so that's basically all you need to do. It's just a sketch, just showing the shape of one complete cycle of a DC generator. Okay, so that's how you would do that one. Okay, so for 9.2.1, it says define the term RMS voltage of an AC source. So we say this is the AC voltage that dissipates the same amount of energy, as an equivalent DC voltage, right? So for 2 marks, that's how you are supposed to define that. Okay, so we've collected marks on conceptual questions, right? So now let's look at a calculation. So as from this, you can see this is now 7 marks, all from conceptual questions. And then you just have that 5 mark for calculation, which at this point you can already see how we go through that, right? So for 5 marks, we already know there are probably 2 or 3 formulas that will be involved. So calculate the maximum or peak voltage of the AC source. Now let's read and see what we have. 9.2 says a 200 ohm resistor is connected to a DC voltage supply. As shown in the diagram, the energy dissipated in the resistor in 10 seconds is 500 joules. The same resistor now is connected to an AC source, which is diagram B, and then 500 joules of energy is also dissipated in 10 seconds. So it's the same conditions in both of them. So calculate the maximum peak voltage of the AC source. How are we going to calculate that? We have the resistance. So let's collect our data. We have resistance, and then we also have energy. Energy is represented as W, the symbol. So that's 500 joules. And then what else are we given? Delta T, so the time in seconds. So what are we trying to calculate? The peak voltage, the maximum voltage. So we do know that in order to calculate the peak voltage, we would first need to get the VRMS, because the formula goes as VRMS is equals to Vmax over root 2. So we can't calculate the maximum without first finding the VRMS. So that means number one, for this 5 marks here, there will be 2 formulas involved. The first formula is to find the VRMS. The second formula is to find the Vmax. So this would have to be the second formula. Now, which one will be the first formula? Based on the data that we have collected, and then we are looking for what? VRMS. Based on this data that we have collected, what formula do we know that has all of this? It's the formula for energy that goes W is equals to V squared IRMS divided by R, then multiplied by delta T. So in your formula sheet, there's such a formula, right? So here for W, that's our energy, 500. And then what is our V squared RMS? That's what we are looking for. But then what is our resistance? That's 200. So you can see how I go about choosing the formula. It's just a matter of collecting the data and seeing which formula will accommodate all of that. Then delta T is 10 here. So what do we do now? We can first cross multiply if you prefer to do that. So let's do it. So we have 500 multiplied by, so 500 multiplied by 200, that's 100,000. And then V squared IRMS, then we have 10 here. So second step, we can divide by 10, both sides. And then if we take that, divide by 10, then we are left with 10,000. But this is V squared IRMS, and then we have 10,000 like that. Then obviously, you put that 10,000 inside the square root so that you get rid of the square here. So square root of 10,000 is what? Is 100. So therefore, our VRMS is equals to 100 volts. But then remember, we are looking for the maximum. So now that's when we use the second formula. VRMS is equals to Vmax over root 2. And then there we go, 100 Vmax over root 2. Then cross multiply this. Then our Vmax is equals to what? .42 volts. There we go, 5 marks. Right. So not a very difficult question as long as you understand what needs to be done. Right. So first collect your data, choose the formula that you need to use, and then analyze what is it that you need to have in order to calculate what you are looking for. Right. So that's the quickest way for you to realize which formula you need to use. Right. So 12 marks in the bag. Let's look at another question. Question 9 says a generator shown below. Assume that the coil is in a vertical position. Note that. Assume that the coil is in the vertical position. Right? So in the vertical position, we already know what happens there. In the vertical position, that's where the voltage or the current will be 0. 9.1.1 says, is the generator above AC or DC? Now, looking at this, we can see that obviously this would have to be what? Split ring, right? So this is a split ring. So we give a reason for the answer. So for 9.1.1, we want to say this is a DC. And then our reason is that it has split rings. Split rings. So split rings, you can see that there is a gap in between the rings there. Then 9.1.2 says, sketch an induced EMF versus time graph for one complete rotation of the coil. the coil starts turning from the vertical position. So if it starts from the vertical position, that means shape will just be like the previous one. So it will start from 0, come back at 0, and then also again there. So it's just a matter of labeling again. This is your time in seconds, and this is your what? Induced EMF. So output voltage, and then in volts, or you can even say induced EMF. So let's just write what they wrote there. Induced EMF. Right, there we go. Then we put the 0 here. Okay, so for 2 marks, that's all you were supposed to show. Then 9.2.1 meant to say, an AC generator is operating at a maximum EMF of 340 volts. It is connected across a toaster and a kettle, as shown in the diagram below. Then there we go. This is a generator. Then there's a toaster, a kettle. Then this one is 800 watts, the kettle 2000 watts. The toaster is rated at 800 watts, while the kettle is rated at 2000 watts. Both are working under optimal conditions. Then calculate the RMS current passing through the resistor. 3 marks. Formula, substitution, correct answer. So how do we calculate the RMS current now that we are given what? The power for the toaster. So P average will be I. So we are given the power and then we are trying to calculate the current. So let's see. Okay, here we are given 340. So we can use this formula now. So we can use this formula VRMS and then multiplied by IRMS. So this is not just a straightforward question like that, because first we would need to calculate the VRMS here. So this is VRMS. Let's start by doing that. VRMS is equals to Vmax over root 2. Then that's 340 divided by root 2. Then let's check what's our VRMS. 340 divided by root 2. That's 240.42. And then volts. Now, we can then use this formula to say that let's calculate the power average. So to then calculate the average power, to then calculate the IRMS, we have the power average. So power average is 800, and then VRMS is 240.42, and then we have IRMS. Remember, this is connected in parallel. So if it's connected in parallel, that means we have an IRMS of 240.42 volts. Also, this one will have a voltage of 240.42 volts. So VRMS will be the same here. VRMS is constant throughout. Remember, it's a parallel connection. Then divide both sides by 240.42. 240.42. Then our IRMS now is going to be what? 800 divided by 240.42. That's 3.33 amperes. Hallelujah. Okay, yes. So one of the long 3-mark questions I've seen. Yeah, so you needed to first calculate the VRMS converted. So by then it's just a matter of conversion. So just convert this to VRMS and then substitute in here, and then you have your IRMS. Okay, so total RMS current delivered by the generator. Now, RMS, right? The RMS. Now, what we can do right now is that we can see that we already have the IRMS for the toaster. So we can simply just do the same thing for the kettle, calculate the IRMS. So P average is equals to VRMS and then IRMS. And then what is our power for the kettle? So let's indicate this is now the kettle. Then this was the what? Toaster. So here we are just using the concepts of electricity to say that we know that in a parallel connection, the current here plus the current here would have to give us the total current, because current is shared amongst the resistors. So remember, with a parallel connection, these are the few things that you need to note. Parallel connection, number one, voltage is the same throughout. Voltage is the same throughout the resistors or the electrical components. Remember, these are known as the resistors. Then a current is divided amongst the resistors or amongst the electrical devices. Right? So if current is divided amongst the resistors, that means with current, if we take the current for the toaster plus the current for the kettle, that means this will give us the total current. So 2000, the VRMS is still the 240.42, as indicated. Voltage is the same throughout the resistors. Then IRMS, then divide both sides by this 240.42. 240.42. Then IRMS becomes what? So let's check 2000, 240.42. Then we have 8.32 rounded off to 2 decimal places. And then now for the total current, for the total IRMS current. So let me write IRMS total. IRMS total. It's going to be 3.33 plus 8.32. And then let's check now. 3.33 plus 8.32. That's going to give us 11.65 amperes. Right. And that's how we tackle that one. So 11 marks in the bag. Okay, so we have this question 10 here. It says, in the simplified AC generator below, the coil is rotated clockwise. The coil is rotated clockwise, and note it is a generator, right? 10.1.1 says, in which direction does the induced current flow in the circuit? Choose from X to Y or Y to X, right? So we did mention that with a generator, if it is rotating clockwise, also the current will be flowing clockwise, right? So that's a clockwise direction. So that means in that case, it will be from X to Y. So you can see that all these questions are the same, guys. Then 10.1.2, on which principle or law is the working of a generator? It is by a Faraday's law of electromagnetic induction. Or you can just say Faraday's law. So this is just writing everything in full. So Faraday's law of electromagnetic induction. Then 10.1.3, state the energy conversion that takes place while the generator is in operation. So we know with a generator at this point, you can even write it in your sleep. Mechanical to electrical energy. If you haven't practiced like this and then you have done as many questions as I'm doing with you right now, you are not prepared, right? So make sure that you always prepare and you see as many questions as possible. It's not a matter of how smart you are, it is exposure. That's the secret of passing exams. You just need to be exposed to as many questions as possible. If you've been exposed to questions, then it means you can't be anxious in the exam, because all you're just going to see are things that you have already done before. So you are familiar with the questions, then how can you be anxious? Then 10.2.1, the voltage output for an AC generator is shown below. So we already know that's our maximum. Write down the maximum peak voltage of the generator. So write down, as you can see that, write down means something that you can see from the diagram, 340 volts. And then 10.2, a stove is connected, 10.2.2, a stove is connected to the generator above and delivers an average power of 1,600 watts. Calculate the RMS voltage delivered to the stove. The RMS voltage, right? Now to calculate the RMS voltage, remember we have the maximum here, Vmax. So we are just going to say VRMS Vrms is equals to Vmax over root 2. Then that's 340 divided by root 2. Punch that into your calculator. That's 240.42 volts. 3 marks. Formula, substitution, correct answer. Then they say now calculate the resistance of the stove. Calculate the resistance. Now to calculate the resistance, based on the data that we are given, power is 1,600 watts. We just recently calculated the Vrms, which we got 240.42 volts, right? And then what are we looking for? Resistance. You see, first collect the data. Then the data will show you which formula to choose. Now, looking at the data and the formula sheet, what formula can accommodate all of this? It is obviously P average is equals to V squared IRMS over R. Voila. Then your P average, 1,600. Your V squared RMS, 240.42. And then square divided by R. Now, it's a matter of cross multiplying here, meaning those ones will swap 240.42 and then square. And then the 1,600 will come over here. The R will come over there. Then 1,600. Now let's calculate resistance. So again, you can see here, formula, substitution, correct answer. That's a 3-mark question. 240.42 square divided by what? 1,600. So our resistance is 36.13, rounded off to 2 decimal places. Ohms. And then again, 11 marks. You can't be anxious when you do this. If you want any magic to pass in your exams, this is the magic. Do marathon questions. As I'm going to do right now, we're just going to be, with all these topics that you're going to write, going to do about 10 or more questions in one video. Use those videos to practice. All right, so we have yet another question 9. 9.1 says AC generator and DC generators differ in their construction and the type of current they deliver. Right. 9.1.1 says, what type of generator is this? AC or DC? Illustrated in the diagram. Now we can see this is a what? This is a split ring. There are gaps in between this, right? So 9.1.1 would have to say DC, right? And then 9.1.2 says state the energy conversion that takes place in this generator. A generator, guys, so it's mechanical to electrical energy. And then 9.1.3, which component X or Y enables this generator to produce the type of current it delivers? The type of current that is being delivered by this generator is direct current. Which component is responsible for that? It is obviously the what? The split ring commutator. So the split ring commutator is being represented by the letter Y. And then 9.1.4 says, will the coil experience a maximum or minimum turning effect if the coil is in the position as shown in the diagram above? So now we can see that this position here is what? Is a horizontal position. And as we have already stated, with the horizontal position, we have the maximum voltage, the maximum turning effect, right? So that means 9.1.4, we want to say what? Maximum. Then 9.2, an electrical device is connected to a generator which produces an RMS potential difference of 210 volts. A what? RMS potential difference, RMS voltage. Remember, potential difference is voltage. Then they say the maximum current, the what? The maximum current passing through the device is 6 amperes. Note how I am careful with reading the keywords, right? And highlighting the keywords so that I don't mess it up. 9.2.1 says, calculate the resistance of the device. Okay, so we have the RMS potential difference, but then we have maximum current. So for this 5 marks, probably involve 2 formulas now. So we need to convert this to IRMS so that we can calculate the resistance. We cannot calculate with the maximum current. So what are we going to do now? Going to say IRMS is equals to Imax over root 2. Then this is going to be what? 6 divided by root 2. And then punch it into your calculator. So 6 divided by root 2. That's 4.24 amperes. So this is the IRMS current. Now to calculate the resistance, we can pull up this formula and then we go VRMS divided by IRMS. Right. Now, there are others who can convert the RMS potential difference to the Vmax, right? And then they use the Vmax and the Imax. Also, that one you can use it to find your resistance. So, but then since in most of the cases, we prefer using the RMS values, I just converted to IRMS. Then, okay, this is going to be R is equals to our VRMS is 210. Then our IRMS now, we're going to substitute the 4.24. See now. So this is 210 divided by 4.24. And then this is going to give us 49.53 watts. Okay. Oh, not watts, ohms. Sorry for that. Yes, so that's our resistance right there. So 5 marks, how many formulas? 2 formulas. First formula to convert Imax to IRMS. Second formula to calculate the resistance. So 5 marks in the bag, just like that. Then let's look at another 5-mark question. So it says the energy the device consumes in 2 hours. 2 hours. Remember our time, delta T should always be given in what? Seconds. So that means we have to convert 2 hours into seconds. Now we know that 1 hour is 60 minutes, and then 60 minutes is how many seconds. So that means we have to say 60 multiplied by 60, and then we find that an hour is 3,600 seconds. But then 2 hours would have to say multiplied by 2. That would be 7,200 seconds in 2 hours. Right. So they say calculate the energy the device consumes in 2 hours. So this is what we are going to do now. To calculate the energy is represented by the symbol W. And then what do we have right now? We have the IRMS, we have the resistance, we also have the VRMS. So that means we can use either one of those formulas for energy. So let me just go with VRMS multiplied by IRMS, then multiplied by what? Delta T. So to calculate the energy, I'm just going to go VRMS. We are given 210. IRMS, we calculated and we got 4.24. And then our delta time should be what? 7,200. Because our time should always be given in seconds and not hours or minutes. So 210 multiplied by 4.24 multiplied by 7,200. So it's going to be a big number, of course. So 6,410,880 joules. That's it. That's it. So others can write it in scientific form. I just wrote it in normal form as it is. So 6,410,880 joules. That is the energy that this consumes in what? In 2 hours. The generator consumes in 2 hours, or the device. Yes, the electrical device. Okay, so we have another question 9. It says the simplified diagram of a DC motor is shown below. The current in the coil is in the direction XY, right? So it is clockwise like that. And then 9.1.1 says, in which direction will the above coil rotate? Choose from clockwise or anti-clockwise. So this is a motor. Note that. Now with the motor, this is what I said. If we are dealing with the motor, if the coil is rotating clockwise, then current is what? Anti-clockwise. This is what you need to note about a motor. And if the coil is rotating clockwise, then that means current will be what? If the coil is rotating anti-clockwise, that means current will be what? Clockwise. Now we can see that this current here is what? Clockwise. The current, so this represents the current. The current is clockwise, meaning that the rotation has to be what? Anti-clockwise. So for 9.1.1, we're going to say anti-clockwise. Because remember, with the motor effect, the rotation of the coil and the direction of the current is in opposite directions. Always note that. Then write down the energy conversion that takes place in a motor. In a motor, it has to be what? Electrical to mechanical. Electrical to mechanical energy. That's it. Then sketch an EMF versus time graph for 2 complete rotations. What? 2 complete rotations of the coil starting from the position shown on the diagram. Right. So the one shown on the diagram is the horizontal position, right? So with the horizontal position, we know that it's at the maximum. So it's producing the maximum EMF. So that means this would have to be how we show the graph. So what we are seeing here is 1 complete cycle. And then for the second one, again, same shape. And then this is the second complete cycle. So these are 2 full cycles. So 0, this is our time in seconds. And this is our what? EMF. EMF in volts. There we go. So these are 2 complete cycles. So it started here because it is at the horizontal position. At the horizontal position, that's where we have the maximum, right? That's where we have the maximum voltage. So maximum voltage all the way like that. And then just like this, it has formed 1 cycle. Again, it repeats the same shape for another cycle. Okay, so 2 marks for that. Nice one. So note the difference if they ask you to draw it from the vertical position and if they ask you to draw it from the horizontal position. If it was a vertical position, then it was just going to be like this. 4 bumps like this. 4 bumps like that. Then the specification of an electric drill are as follows: 2100 watts and 230 volts. Then define the term root mean square potential difference. Define. So root mean voltage or potential difference. So let's say root mean RMS potential difference is the AC potential difference which dissipates the same amount of energy as an equivalent DC potential difference. You see, I'm manually writing this because this is what I want you to also get used to. With the definitions, do not study them the day before. While you are practicing your questions, when you see those definitions, make a culture of writing them always. When you've written that definition for more than 5 times, there's no way you're going to forget that definition. So RMS potential difference is the AC potential difference, which dissipates the same amount of energy as an equivalent DC potential difference. Then 9.2.2 says calculate the maximum value of the current that can flow through the drill, right? Maximum value. So we are looking for what? The Imax. So what are we given here? 2100 watts and 230 volts. This is the VRMS. So if they give you specification for an electric device, always note that the voltage or the current that will be given there is always the root mean square, right? So to calculate the maximum current for this, we have to apply two formulas. Then the first formula is to find the IRMS. Then from finding the IRMS, we can then use the second formula to then calculate the Imax, right? So with the data that we are given here, power average is 2100 watts, and then the VRMS is 230 volts. So always note that if we are given specification for any electrical device, and then they give you the voltage, that voltage is definitely the VRMS. And if they give you the current, that current is definitely the IRMS. So what are we looking for now? It's first the IRMS. Now looking at what we have here, what formula can we choose? So note how I go about choosing the formula. First, you collect the data and let the data decide for you. So this is P average is equals to VRMS multiplied by IRMS. The P average, 2100, VRMS, 230, IRMS, we don't know. That's what we are looking for. So divide both sides by 230 like that. Then our IRMS is equals to what? So 2100 divided by 230. So this is going to give us 9.13 amperes. And now to calculate our maximum, we're now going to apply the second formula over root 2. Then this is 9.13 Imax over root 2. Cross multiply there. Imax is equals to what? (9.13) multiplied by root 2. This is 12.91 amperes. That's your maximum current. So 10 marks in the bag. All right, so we have another question 9. It says, study the diagram below and answer the questions that follow. 9.1 says, what type of generator is shown in the diagram below? Motivate the answer by referring to the names of specific components in the diagram, right? So what type of generator is shown here? So we can see that this has to be a what? An AC generator. And then it is what? Because it has slip rings. Right, so it's an AC generator because it has slip rings. Okay, then 9.2, indicate the direction in which the current will flow in section AB. Note that this is a generator, and if it is a generator, we can see that the rotation of the coil now is in a clockwise direction, meaning current must also flow in a clockwise direction. So this would be the clockwise direction. This would be the clockwise direction. So in that manner, that means in 9.2, it would have to be from B to A. B to A. Then 9.3 says the following graph is obtained from an AC generator. How many rotations of the coil are shown in the diagram? So 9.3.1, how many rotations of the coil are shown in the diagram? This is a full rotation. This is one rotation, because as we can see, this is a full sine wave, right? And then this is a half rotation. So that's 1.5. 1.5 rotation. That's a 1.5 rotation. Then 9.3.2 says, define RMS current. So RMS current is the AC current that dissipates the same amount of energy as an equivalent DC current. Right. Then 9.3.3 says calculate the average power that can be delivered by this generator to an apparatus with a resistance of 30 ohms. So what are we given there? Remember, this is the graph for current versus time. So this means this represents the maximum current, not Vmax, the maximum current. Now they say calculate the average power that can be delivered by this generator to an apparatus with a resistance of 30 ohm. Now we have Imax. This is a 5-mark question. So we know that in order to find the power, we would have to first convert the Imax to IRMS. So for 9.3.3, first it's IRMS. So first formula is Imax over what? Root 2. Then that will be 15 divided by root 2. Then let's punch that into our calculator. We have 15 divided by root 2. So this is going to give us 10.606. So let's just say 61 amperes. Then to then calculate the average power, P average, let's just go with IRMS square, I squared IRMS, then multiply that by R. So our average power, we want to calculate it by saying 10.61 and then square. But then I'm just going to keep the answer from the previous question here because I don't want to round off, and then 30. So if I take that value, and then multiply by 30, then what am I going to get? So 10.61 square multiplied by 30, that's 3,377.16 watts. Okay, for the sake of the question, let's just use this, 10.61. So 3,377.16 watts. That's the value that we get from using this value that is rounded off there. Okay, then an electric hair dryer is rated at 2,200 watts at 240 volts. Remember, an electrical hair dryer is an electrical device, so that means the 240 here is representing the what? The VRMS. Assume that the hair dryer is a pure resistor. Calculate the maximum current that flows through the hair dryer when it is used. Calculate the what? The maximum current. So now they're looking for Imax, right? So we do know that the first thing that we have to calculate is the IRMS. And then we're going to use the IRMS to then calculate the Imax. So you get the drill right now. So this is P average is equals to VRMS multiplied by IRMS. Our P average, 2,200. Our VRMS, 240. And then here we put IRMS. Then if we divide both sides by 240, there we go. 2,200 divided by 240. Our IRMS, let's now see, it's going to be 2,200 divided by 240. So this is going to be 9.116, let's say 167 amperes. And then let's use it to calculate the maximum now. Imax over root 2. So this is 9.167 is equals to Imax over root 2. So our Imax will now be what? 9.167 multiplied by root 2. This is going to give us 12.96 amperes. Voila. So this one was a bit longer, 17 marks, right? So 17 marks. All right, so we still have another question 9. It says the diagram below is a simplified representation of a generator the coil is rotated clockwise. Then they say, is there above a DC or an AC generator? Looking at this, we can see that these are what? Slip rings. So with the slip rings, we have to say this are what? This is an AC generator. This is an AC generator. Then 9.1.2, they say write down the name of the component X. So these are what? Slip rings. 9.1.3, they say write down the function of component Y. So component Y, these are what? These are carbon brushes. So carbon brushes function is carbon brushes ensure conductivity, electrical conductivity between the slip rings and the external circuit. Yes, so it ensures electrical conductivity between the slip rings and the external circuit. Then 9.1.4 says, is the direction of the induced current from P to Q or Q to P? So this is a generator once again. It is being rotated clockwise, meaning that current will also flow clockwise. So this has to be what? P to Q. Then 9.2 says the graph below shows the output voltage from a household AC generator for the rotation of the coil for one complete cycle. 9.2.1, they say the speed of the rotation is doubled. Sketch the graph of the induced EMF versus the time for the change for one cycle. Indicate the maximum voltage and relevant time values. Now, if the speed of the rotation is doubled, we know that according to this formula now, if we increase the speed, we are actually doing what? We are actually decreasing the time, right? Which will then do what? Increase the EMF. So if we double the rotation of the coil, then that means even the EMF is supposed to do what? To double, right? But then what will happen to the time? The time will halve. So how do we indicate that? So that means that this is the graph that is supposed to be what? Compressed. This is the type of graph that is supposed to be compressed. So with a larger amplitude now, compressed with a larger amplitude. So note that here, the period was 0.02. So it took 0.02 to complete one full cycle. So that means if we say the time will halve, even the period will halve to 0.01. So that's our time in seconds. And then here we have output voltage. Output voltage is given in what? In volts. Note that we said that the EMF will double. So here we had 311.13. So if we double that, what is it going to be? 311.13 multiplied by 2. It's going to give us what? 6.22.26. So even here, I have to indicate negative 6.22.26. So there we go. We have our 0 there. And then we just indicate that. So this is what they are going to check here. For that 3 marks, they are going to check whether you indicated the fact that here you have to have this 0.01. And then you have indicated your maximum values. And then also the graph is compressed with the same shape. Right. Okay, so that's what happens. The EMF doubles and the period halves. Right. So for 9.2.2 now, they're saying an electrical device is connected to this generator. And then the maximum current passing through the device is 8 amperes, right? Is 8 amperes. Note it is what? The maximum current. Now they say calculate the resistance of the device. The resistance of the device. So, okay, now we can just say to calculate that, can just say this is R is equals to what? Remember, I did say that you can also calculate with your maximums, Vmax over Imax. So our Vmax is 311.13, and then our Imax is 8. So we can find the resistance simply just by doing that. So 311.13 divided by the maximum of 8. So this is going to be 38.89 ohms, right? And then that's your A. So for 4 marks, that's what you do. And then now they want the energy the device consumes in 2 hours. Again, the 2 hours. Remember, we did convert the 2 hours and we said we are supposed to say 2 multiplied by 60, which end up giving us 7,200 seconds, right? So to calculate the energy, the formula, just going to go W is equals to what? So we can convert both the maximums. So we're going to have VRMS multiplied by IRMS, then multiplied by time, right? So let's start by converting VRMS. So Vmax, converting Vmax to VRMS, meant to say, then this is going to be what? 311.13 divided by root 2. 311.13 divided by root 2 is going to be 220 point. Okay, just 220 volts. And then let's now do IRMS. So it's going to be Imax over root 2. And then this is going to be 8 divided by root 2. So all of this is part of B. And then this is 8 divided by root 2. It's going to be 5.66 amperes. Then let's calculate the energy. 220 multiplied by 5.66 multiplied by 7,200. So what is the energy now? 220 multiplied by 5.66 multiplied by 7,200. So that is 8,965,440 joules. Nice. Okay, so there we go. So right, that's how you were supposed to tackle all those questions. So still going to post more of the questions, but then for now, let's just stop here. I think it's a pretty long video for now. So, okay, just go through all those questions. Try to understand the approach that I took into answering all those questions. And then most importantly, see the trend of the questions, right? Once you get the trend, then it becomes very easy to tackle your questions, right? So you know what to expect. With all that being said, guys, please press that subscribe button if you haven't subscribed yet. And then if you have already subscribed, press that like button, comment anything on the comment section. You can just say the video was dope. You can just maybe ask a question where you didn't understand. I will see the comment and try to clarify, guys. Okay, so with all that being said, guys, see you on the next episode. Ciao, ciao.